Good afternoon, class. We are looking at the statistic practice test number 5, covering chapters 10, 11, and 12. Here's chapter 12, analysis of variance. One-way analysis of variance, ANOVA, is used for test of hypothesis that 3 or more populations have means that are all equal, as in H0, mu sub 1 equals mu sub 2 equals mu sub 3, by analyzing sample variances. One-way analysis of variance is used with data categorized with one factor or treatment, so there is one characteristic used to separate the sample data into the different categories. The populations have the same variance, sigma squared, or standard deviation, sigma. Could you please read that?
In the F test for analysis variance or ANOVA, two different estimates of the population variance are made. The first estimate is called the between group variance and involves finding the variance of the means. The second estimate, the within group variance, is made by computing the variance using all of the data and is not affected by differences in the means.
Please continue.
If there is no difference in the means, the group between variance will be approximately equal to the within group variance, and the F test value will be close to 1. Do not reject the null hypothesis. If the means differ significantly, the between group variance will be much larger than the within group variance. The F test will be significantly greater than 1. Reject the null hypothesis.
All right, so in essence, we're using the F test, which has the test statistic S1 squared over S2 squared. So the ANOVA test is right-tailed because only large values of the test statistic cause us to reject equality of the population means. Other statistics test, Shafee test, and Tukey test are used to find where the difference exists, although the t-test is commonly used to compare two means. It should not be used to compare 3 or more. In short, if you have more than 2 means, you use the analysis of variance. So here's an example. Weights in kilograms of cypress trees were obtained from trees planted in a sandy and dry area. They were given different treatments as indicated in this table. Fill up the table below. This is an ANOVA table. And use a 0.05 significance level to test the claim that the 4 treatment categories or factors yield cypress trees with the same mean weight. So what's happening is that we have in this category no treatment. We give fertilizers here, irrigation here, and fertilizer as well as irrigation for the last one. So the very first thing we need to calculate would be the count. That means the size, the sample size. Then there's some average variance. So obviously 1, 2, 3, 4, 5. So the count or n is 5, and it happened to be the same for all of them. The sum, you just add them up. So you add them up. You can divide by 5, and it gives you the X bar for this group, and the same thing you do for the next and the next and the last one. Finally, you calculate the variance for each group, all of which basically are done by technology. So just as an example, what does this mean? The first group with no treatment has a count of 5 with a sum of 5.95. That means 0.24 plus 1.69 plus 1.23 plus 0.99 plus 1.8. That's the meaning of it. Divide by 5. That's the X1 bar. And the variance using the summation of X minus X bar over n quantity squared over n minus 1. The same thing for the second group, third, and fourth. So there are 4 groups, and we are looking at the x bars. We want to see what's happening. The bottom line is we want to see if they, according to the calculation that we have based on the x bars and the variances, are they providing, yielding cypress trees with the same mean. So we have to fill up this table. So let's look at some calculations, and bear in mind, it's almost always calculated using technology. So the first thing I want to look at is the GM stands for the grand mean, X bar of grand mean. That means regardless of how many pieces you have, add them up, divide by size. So the first one is 0.24, 1.69, all of it to the last one, which is 0.95, and you have 4 times 5 or 20 pieces. Add them all up, and divide by 20. That's the average. And we call it X bar GM because it's the average for everything, every piece of data. Then we have the sum squares in between, n sub I times x sub I bar minus x sub the grand mean. So in this case, for example, for this one, n is 5, that means n sub 1 in essence. Then it would be x sub 1 bar, which is 1.19, minus the grand one, which is 1.0935, and then square it. Then plus the second one is also 5, the n, 5 times this number now, x2 bar minus this quantity squared, plus 5 times the parentheses, this bar minus this one squared, and the last one. So that's how you calculate it. And again, this is not done by hand, but you have the SSB, the sum of squares in between, it's called, between treatments. And so we put the number in here. The next one is understanding degrees of freedom, k minus 1, 4 minus 1. We have a 1, 2, 3, 4, or k categories. And so k minus 1 is 3. And n minus k, 20 minus the number of categories is 16. In other words, each group minus 1, n1 minus 1 plus n2 minus 1 plus n3 minus 1 plus n4 minus 1, or simply put n minus k would be 16. And this is where you put them. And the last one obviously would be the sum of these two numbers. In other words, if you look at this column, any of them missing, you should be able to find it. So this is 3, this is 16, add them up 90. So this one, when you go to the next column, you divide it by k minus 1, meaning you divide this number by number 3. And we put it here. Now let's calculate this one, SS, the sum of squares within W. And so it's n sub I minus 1 times s sub I squared. Since we have already calculated this, we're going to multiply this one by n sub 1 minus 1, so 5 minus 1. Plus, we're going to multiply this one by 5 minus 1, whatever this number is. And normally, we like to use the same sample size. And therefore, so in all cases, this 5 becomes 4, right? 5 minus 1. And then times this, plus 4 times this, 4 times this, and 4 times 0.1901. I have rounded. And so that becomes sum of squares within, and we put it here. And of course, sum of square total is the sum of the two numbers. Sometimes if you, again, one is missing, you can find the missing one. Understand the sum of these two must be equal to last. Now, in this case now, we divide the number that we have by 16, this number divided by 16, or capital N minus 1, n minus k. This should be n minus k. This is n minus k. And so we have the answer 0.271373. Now, as far as the f is concerned, is the ratio of these two numbers. And in essence, this is the standard deviation, so is this one. The standard deviation between treatments, standard deviation within treatments. And it's 0.3897, you put it here. As far as the p-value and a critical value for f, when we use the technology, this table is given to us. First, so I wanted you to have an idea how it's calculated. Now let's go with the same question, and let's say the table is created by some sort of a technology. We went through the calculation by hand, but technology will provide that for you. And again, if anything missing, you can find it. For example, this number is missing, 19 minus 3 gives you 16. You should know that. So H0 mu sub 1 equals mu sub 2 equals mu sub 3 equals mu sub 4. Why 1, 2, 3, 4 categories? That is the claim. At least one of the treatments has a population mean that is different from the others. And we take it to be RTT, right tail test. Look at this value. This is the test statistic. It's been calculated by us, the previous page, or technology. This is the critical value given to us by technology. If we wanted to find it from the table, number of groups or factors is 4. Degrees of freedom of the numerator is k minus 1. 4 minus 1, 1, 2, 3, 4 minus 1 is 3. And degrees of freedom of the denominator is n minus k, or 16. And from the table, we get the same answer with a lot more decimals when it comes to technology. And we can also see the p-value. The p-value clearly is larger than alpha of 0.05. And if we were to go with the graph, this is alpha of 0.05. This is where the test statistic is, which puts us way into the non-rejection region. Therefore, fail to reject H0. Fail to reject H0, what does it mean? The claim is true, and there is sufficient evidence to support the claim that 4 population means are all the same. So fail to reject H0, the claim becomes true, and there is sufficient evidence to support the claim that 4 population means are all the same. We conclude that the 4 treatments do result in cypress trees with the same weight. It makes no difference which one we use, according to the given information. Given the readability scores summarized in the following table and a significance level of alpha equals 0.05, use technology to test the claim that the 3 samples come from populations with means that are not all the same. We are looking at reading from different writers, Clancy, Rowling, Tolstoy, and so we have to calculate n, x bar, and s, so for each group, and n is 12 for each one. We calculate the x bar, add them up, divide by size. We calculate the s, and here's the Excel source. It could be from any other sources. It is just a matter of using the technology. And again, just for the sake of argument, notice these 2 add up to this number, these 2 add up to this number, and the ratio of these two numbers is this is the p-value, this is the critical value. Everything is there. Let's do the writing. H0, mu sub 1 equals mu sub 2 equals mu sub 3. Why? There are only 1, 2, 3 different riders. At least one mean is different from the others, right tail test or the claim. And look at the test statistic. So we write the test statistic from the table. Critical value, we write it from the table, and we can also use the fact that the degrees of freedom of the numerator is 3 minus 1 or 2, the denominator is 36 minus 3 or 33. And again, from the table, not this table, the F distribution table, this is from this table, that is the technology table. And we have the same answer, of course, more decimals again. And if we look at the p-value, clearly it's much less than alpha of a 0.05. And even if we look at the graph, we notice that this number is way larger than the critical value, puts us way into the rejection region. So you reject H0. So what happens when we reject H0? Loosely put, we accept H1 and the claim becomes true. And so they don't have the same readability, in short. So reject H0, the claim is true. There is sufficient evidence to support the claim that the three population means are not all the same. We conclude that those books have readability levels that are not all the same. If you were to use TI, you go with one-way ANOVA. You first clear the list, however many lists, L1, L2, L3, and then you run ANOVA with those. So we have cleared them and we put the numbers, for example, 58.2, 73.4 all the way to the end, 85.3 to the end, 69.4 to the end, and now we just run ANOVA with L1, L2, L3, and it gives us some information. Let's see what they are. After we run them all, take a look at these values. So this is the same test statistic we found. Look at this one. This is the p-value, and by the way, 5.6213335 e minus 4, that means times 10 to the power of -4, the same as this one. Notice these numbers are calculated here. The sum of squares in between and the mean square, in essence, the standard deviation. So similar calculations for in between. And then we have the within numbers also calculated here. Look at the degrees of freedom. Sum of squares, everything else, MS 70.64. And all the calculations are here. You can use either technology.